Let's solve another problem involving a polytropic process. This one in which the polytropic process is just one of several processes that are in series. This problem seems to have a complex explanation, but we'll find that when we lay out our storyboard that it's really not as difficult as it might appear. So let's dig into it and see what we've got. A gas contained within a piston cylinder assembly undergoes three processes in series. Now, these processes do not form a cycle. Process 1, 2 is a constant volume process from P1 equals 1 bar, V1 equals 4 cubic meters, to state 2, where P2 equals 2 bar. Process 2, 3 is a compression process ending at V3 equals 2 cubic meters, during which the pressure volume relationship is PV equals constant. So that is our polytropic process with N equals 1, since PV to the N power equals constant. Process 3-4 is a constant pressure process to state 4, where V4 is 1 cubic meter. We want to find the work done by each of these processes. Let's start with by defining the system in a schematic. We have a piston cylinder assembly containing a gas, and the boundary I've drawn is just around the gas. So the gas is the system, not the cylinder. All right, and we have multiple processes in series. So let's look at what they are. I always like to make a table of all the given data. And what we have is we have 4 states and 3 processes that connect them. Now we know state 1 is 1 bar and 4 cubic meters. And we know state 2 is 2 bar, and the volume is also 4 cubic meters, because process 1, 2 is a constant volume process. Now process 2, 3 is our polytropic process, PV equals constant. Okay, taking us to state 3, where we do not know the pressure, not yet, but we do know the volume at state 3 is 2 cubic meters. And finally, process 3-4, which is a constant pressure process, takes us to state 4. So P4 is equal to P3, although P3 is unknown. But the volume at state 4 is 1 cubic meter. Well, now that we've laid this out, let's draw it, and we can visualize this even better. We know state 1, so state 1 is here at 1 bar and 4 cubic meters. And process 1, 2 is a constant volume process. So it's going to be a vertical line on our PV drawing. And we see that at state 2, we have a pressure of 2 bar, and we're still at 4 cubic meters. Now the next process 2, 3, is our polytropic process. And since N is neither 1 nor, it's neither 0 nor infinity, N is actually 1, we'll draw it as a concave line to state 3. Now we don't know the pressure at state 3, but this line will curve upwards until we reach a volume of 2 cubic meters, because that is given as the volume at state 3. And finally, the process 3-4 is a constant pressure process ending at a volume of 1 cubic meter. So we can draw that as a horizontal line on our PV diagram. So the only thing unknown about this diagram, we do not know the pressure at state 3 or state 4. We know they're identical, but we don't yet have a value for them. We can create an engineering model. We're dealing with a closed system. We'll assume there's no change in kinetic or potential energy during these sequence of processes. And we're going to define precisely what it is we want. We want to find the work done by each of these 3 processes. In order to continue, we need to find the pressure at state 3, which is also the pressure at state 4. And we're going to do this by looking at the polytropic process. We know that PV to the 1 power is equal a constant, so we can say that P2V2 is equal to P3V3. Well, we want to solve for P3. It's the only unknown variable. And that's going to be P2 times V2 over V3. Now we have all of these values. We can put them in, and we solve for P3, and it is equal to 4 bar. Let's find the work of each process. Now, we know that work for a given process is the integral of P to V. And we have already solved this integral in previous problems and for various situations, and have turned them into algebraic expressions. So we don't have to continue to do integral calculus in solving these problems. But this one is trivial. The work is the integral of P to V, but to V is equal to 0 in a constant volume process. So the work of process 1, 2 is 0 kilojoules. Now, for the polytropic process, we have already integrated P to V for a polytropic process where then n equals 1. And you will recall that we got that it was P2V2, in this case at least, times the natural log of V3 over V2. Well, we have these values. We know P2 is 2 bar and V2 is 4 cubic meters. And we have V3 and V2. And we'll use our unit conversion factor of 1 bar cubic meter is equivalent to 100 kilojoules. And so we see that the work of process 2.3 is minus 554.5 kilojoules. Negative indicates that in order for this process to take place, work must be provided, we must do work on the system in order to get the process to take place, because we are in this process increasing the pressure and decreasing the volume of the gas. And in the final process, we also have the integral of P to V, but this is a constant pressure process. And we've solved that integral before as the pressure of the process times the change in volume. Well, for this process 3.4, we have a pressure of 4 bar, and it starts at 1 cubic meter and it ends at 1 cubic meter and begins at 2 cubic meters. So we have 1 cubic meter minus 2 cubic meters. Again, converting to kilojoules, and we find that the work done in process 3.4 is minus 400 kilojoules. So in order for this process to take place, work must be done on the system.